Let me share the screen. Okay, start the presentation. So last lecture started from classification, types of passive filter based on band of frequency, low pass, high pass, band reject. We discussed low pass filter, its characteristics, cutoff frequency, an expression for critical or cutoff frequency, V out upon V, derivation for V out upon V, general guidelines. And then some numerical problems. Okay. And this is the high pass filter. Okay. As the name suggests, it passes high frequencies and rejects or blocks the low frequencies. What is the difference between circuit of high pass and low pass? In low pass, there is resistor, there is capacitor. In high pass, the positions of resistors and capacitor are interchanged. R here and C here. Okay, it will pass the low frequencies and block high, whereas C here and R here will pass the high frequencies and block the low frequencies. How is it possible? Due to the same reason, X is inversely proportional to F. Okay, we want to pass high frequencies, and how they are passed then? For high frequencies, X is equal to 1 upon F 2 pi Fc. F being high, Xc will be very low, and whatever frequency input signals are there, high frequency input signals are there, they will be easily passed to the output. Whereas for low frequencies, 1 upon 2 pi Fc, F being very low, Xc will be very high, and those amplitudes of output amplitude of those low frequency signals will be very less when they are blocked by this capacitor. Okay, so this way the circuit containing C in series and R in parallel works as high pass or high pass filter circuit. This is the ideal characteristics. Okay, this is the stop band, what we call it as. This is cutoff frequency, and this is the pass band. So below the frequencies below cutoff frequency are rejected, blocked, or stopped from going to the output, whereas high frequencies above cutoff frequency are passed through a filter circuit. Okay, so we know for practical circuits this exact and strict cutoff is not possible. Okay, instead we get a slanting characteristics like this. Okay, so in this characteristic we see that this is the stop band and this is the pass band, and we define the cutoff frequency in practice as the frequency corresponding to output V upon Vi to be 0.707 on 1 by root 2. So this frequency corresponding to 0.707 is taken as cutoff frequency. Okay, definition will be similar to that we have defined already in low pass filter. So this is the characteristics on logarithmic. Here it is drawn on simple frequency, right? Here it is F upon Fc, okay, and that too on semi-log paper. This is logarithmic scale, this is linear scale, right? So we get such a characteristics, and at 0.707, whatever the frequency, F is equal to Fc, F upon Fc will be equal to 1, and which will be 0.707. So this is cutoff frequency. Okay. So how is the cutoff frequency given by? Cutoff frequency is given by same expression as in low pass filter, 1 upon 2 pi RC, and the ratio of output to input signal is given by V out upon V is equal to F upon Fc divided by root of 1 plus F upon Fc square. Okay. In case of low pass filter, the numerator was 1. That only is the difference. In a high pass filter, the numerator is F upon Fc. In case of low pass filter, it is 1. Okay. F is the given frequency here at which we want to find out V out upon V in, whereas Fc is the cutoff frequency. Okay. Next, let us derive cutoff frequency that we have already seen. The formula comes out to be same, but we want to derive it. Okay. We know this is RC circuit is voltage divider circuit, something like this, with Xc and R. Output is taken across R, and therefore it will be R upon R plus Xc into V in, right? So V out is equal to R upon R minus Jxc into V in, or R upon R root of R square plus Xc square. Okay. For Fc, V out upon V in should be 0.707, right? So 1 by root 2 or 0.707 is equal to R upon root of R square plus Xc square. Squaring both sides, I get 1 by 2 is equal to R square divided by R square plus Xc square. So solving this, we get Xc square is equal to R square, or 1 upon omega square C square is equal to R square, or omega square is equal to 1 upon R square C square. Omega is equal to 1 by RC, and so Fc comes out to be the same as in case of low pass filter, 1 upon 2 pi into RC. So same expression for high pass and low pass RC circuits. Okay, let's derive the expression for V out upon V in for of high pass circuit. Right, V out upon V in, we know V out is given by this into V in. So V out upon V in is R upon root of R square plus Xc square, right? So R upon root of R square plus 1 upon omega square C square. Simplifying, we get this omega RC divided by root of 1 plus omega R square R square C square. But this can be replaced by omega 1 upon omega C, because we know that omega C is 1 by RC. So RC is equal to 1 by omega C. RC is equal to 1 by omega C. Substituting it here, it will be omega square upon omega C square. Omega C square. So it is 2 pi f whole square divided by 2 pi f c square. So it cancels out, and what we get is simplified formula as V out upon V in is equal to F upon Fc divided by root of 1 plus F upon Fc whole square. Right? So this is how, what are the formulae in this case then? Fc is given by this and F is given by this formula. Let's compare with these formulae with low pass filter. Fc is same, whereas for low pass filter it is numerator is 1. Denominator remains same, numerator is 1, whereas in case of high pass filter, we get numerator to be F upon Fc. That is the difference then. Okay. Okay, we derived this one. Let's solve some example based on this one then. Okay, take pen and paper, notebook then with calculator. Okay, notebook, pen and calculator. What is the problem? Pulses for stepping motor are being transmitted at 200 kilohertz. Design a filter to reduce the 60 hertz noise. F is equal to 60 hertz, but reduce the pulses not more than 3 dB. Okay, 3 dB corresponds to 0.7. V out upon V in is equal to 0.707. Right? So this frequency corresponding to this is cutoff frequency, right? So let's call it. Uh, Start the slideshow. I did not start actually. Okay, the noise is to be reduced by 3 dB, and the 3 dB corresponds to V out upon V into V 0.707, and frequency corresponding to this value of V out upon V any cutoff frequency. Okay, so FC is given as 2 kilohertz. Okay, and we know that for high pass filter, V out upon V in is given by F upon Fc into root of 1 upon Fc whole square. So V out upon V in, F is given as 60 hertz. Okay, nice to be found out at 60 hertz. So 60 upon 2000 divided by root of 1 plus 60 upon 2000 whole square, and this comes out to be 0.03. Thus, at 60 hertz, only 3% noise remains. That is 97% of noise is reduced at 60 hertz. Okay. Now let's design it. Let's find out the values of R and C. Okay. As per the previous guidelines, same prevail for this also. Okay. Let's consider the capacitor to be 0.01 microfarad, and substituting in the critical frequency or cutoff frequency, Fc is equal to 1 upon 2 pi Rc. So R is equal to 1 upon 2 pi Fc into C. So substitute it, 1 upon 2 pi into 2000 into 0.01 that we have already considered capacitor into 10 raised to minus 6. So R comes out to be 7.957 kilo ohms. Okay. Exact this value will not be available in the market, and the nearest standard value 7.5 or 8.2 kilo ohm. If I substitute it here, okay, substitute in the formula Fc is equal to 1 upon 2 pi Rc with modified this value or this value. Okay, tell me the value of cutoff frequency. Tell me the value of cutoff frequency for 7.5 and 8.2. Okay, calculate and tell me what will be the cutoff frequency corresponding to 7 R is equal to 7.5 K and 8.2 K. Both values I want. Okay, tell me, and whether this FC will satisfy this criteria. 0.03. Okay, at this FC and for this FC and this FC, whether this 0.03 criteria is satisfied, 3% noise is reduced or not. Okay, I want that. So calculate FC for this and FC for this and tell me. Okay, you can write your answer in chat box. Yes, I'm waiting. Substitute R is equal to 7.5 kilo ohm in formula for FC and calculate FC. Similarly, find out FC for R is equal to 8.2. Type the answer. Yes. Rishikesh. Rishikesh.
Yes, sir.
Um, uh, Put on your video audio also. Get me the answer.
Yes, sir, solving.
Neha, are you there, Neha?
Yes, sir.
What is the answer? Tell me.
Yes, solving, sir.
सर आन्सर काय येतं का?
Huh?
आन्सर गिगाहर्ट्ज मध्ये येतं का कट ऑफ फ्रिक्वेन्सी?
No, no. It should not be because what is the difference? Okay. What is the difference? What we have actually found is 7.95 and I have given 7.5. There should not be much difference in frequency. Frequency is 2 kilohertz. So it will be slightly less or more than that.
So that standard value 7.5 ka, that's resistance, right?
Yeah.
Okay.
Instead of 7.95, you have to put 7.5 for first case and 8.2 for second case. What I want to check is whether this satisfies this criteria or not. This criteria 0.03. Okay. For this FC and for this FC, if I choose this or choose this, whether this criteria is satisfied or not. 97% reduction and 3% noise remaining. Okay. Otherwise, I have to choose exactly this value using potentiometer also. Instead of choosing this standard value like this or this, I have to choose a potentiometer 0 to 10K and adjust this value each time to 7.957K. Okay, that's what I want to check whether if suppose with this value and this value, I am getting V out upon V in as 0.03, then well and good, no, not necessary to use the potentiometer also. I can use this standard value. That's what I want to check. So what answer I'm getting? Still no answer. Yes. Rishikesh, Vishal, Pranav, Neha, Omkar, Aras, Prajwal, Sandhya, Saurabh, Shweta, Vinkita, Vibha, Vishal. Are you there or not? Why you are taking that much time? What happened on the 0.8 and 0. Are these values correct? Getting the same answer. Saurabh, Devishri is getting 0.8 and 0.54. Should not be like that, I think, because the resistance value is not changed that much. There should be some calculation mistakes, I think. Changing the resistance from 7.9 to 7.5 or 8.2 would not drastically change the values from 0.03 to 0.8. Yes. What is the value of FC? For 7.5K, I am getting it to be 1.122, 2.122 kilohertz. Okay, 2.122 kilohertz FCS. And for 8.2 kilohertz, I am getting 1.940, 1.941 kilohertz. Okay, so with this FC, I think there should not be any problem in getting V out upon V in around 0.03. So it should not uh, drastically change. Devashri, have you checked? Okay. So they satisfy this, right? Next, second example, an high-pass RC filter must drive 120 hertz noise down to. What I think is you are not ready with. Shall I ask you to put on your video? No one is responding except for Pranav, Devashri, Saurabh. Okay, I'll call and ask you by name. Put on the video then, right? So let's go to the second example and try to solve this then. Try to solve it on yourself then. What is given? F is given as 120, whereas the noise is to be down to 1%. 1% meaning 1 upon 100, 0.01. So V out upon V in is given as 0.01 and F is given as 120. Find the critical frequency and assuming any suitable value of C, find the value of R. And then substituting F is equal to 30 kilohertz in the formula V out upon V in, find out that V out upon V in. Okay, solve this one. I'll ask you to put on the video and then we'll check your notebook. Yes, are you solving? Are you there? Yes. Solve it. Rishikesh. Rishikesh, put on the video. Are you listening to me? Rishikesh? Rishikesh, are you there? Okay. Put on your video. Okay, solve it and tell me. Yes, Neha. Neha, put on the video. Neha Bacha. Neha, are you there? What answer you are getting? What is FC? Unmute. Tell me the value of FC.
Sir, I have not noted down the question. Can you once again show that question?
Okay. F is given as, in first case, F is given as 120 hertz and V out upon V in is given as 1%. That is 0.01. Just substitute the value V out upon V and find out. Yes, Rishikesh. How much time you will require? Priyanka, put on the video, Priyanka. What answer you are getting?
Sir, driver.
विशाल झालं का रे? सौरभ किती आला आन्सर? देवश्री, are you calculating? अरे ऋषिकेश काय करतोय? एवढा अवघड कॅल्क्युलेशन नाही आहे ना रे.
सर कॅल्सी नाही माझ्याकडे.
घरीच आहेस ना?
हो सर, पण दुसऱ्या
पाहुण्यांच्या घरी आहेस?
कॅल्सी दुसऱ्या रूम मध्ये आहे.
घेऊन येत जा.
हा सर, आणतो.
घेऊन ये. हे अगोदर नाही सांगायचं तर वाट बघत बसतो. विशाल वीडियो ऑन कर रहे हैं। सौरभ, प्रणव, वीडियो पुट ऑन करा। प्रणव आहेस का? 1.2 किलोहर्ट्ज देवश्री गेटिंग.
काढतोय सर एक.
अरे काय इतका वेळ कशाला लागतोय?
सर माझं कॅल्सी खराब झालं, तुम्ही फोनच्या कॅल्सीवर करतोय तर ते थोडा प्रॉब्लेम होतो जरा त्याच्यावर.
सौरभ तुझं किती आलं ते आन्सर? विशाल कुठे गेला? विशाल आहेस का झोपला? एवढं कठीण वाटण्याचं काही कारण आहे का? मागचा प्रॉब्लेम सॉल्व्ह केला तसंच आहे ना जास्त. सेमच प्रॉब्लेम आहे, फक्त जसे त्याच्यामध्ये व्हॅल्यू ठेवायच्या फॉर्म्युल्यामध्ये. काय झालं नेहा, प्रियांका, विशाल कुठे गेला? आहेस का रे? कशी अटेंडन्स लागणार विशाल? ऍबसेंट मार्क करू का? फिल्टर्स डिझाईनवर टेस्ट घेणार आहे मी या आठवड्यामध्ये.
सर क्वेश्चन दाखवा.
क्वेश्चन
क्वेश्चनची स्क्रीन 2 मिनिटं.
अरे काय करताय काय? ऋषिकेश कॅल्क्युलेटर आणायला काय दुकानात गेला काय? बाजारातून विकत आणतो काय ऋषिकेश?
सर आणलं मी कॅल्क्युलेटर बट चालत नाही.
ते पण चालत नाहीये.
नाही सर.
तुझं नेहमीच आहे ना?
हा सर मी वापरतो बट ते आता मे बी खूप दिवस वापरलं नाही म्हणून खराब झालं सर.
सर माझं पण खराब झालंय तसंच, बरेच दिवस काहीतरी झालं ते.
अरे बघा.
नेहा तुझं चालू आहे का प्रियांका? कॅल्क्युलेटर चालू आहेत का तुमची पण खराब झाली 6 महिन्यात? सगळ्यांची एकदम खराब झाली आहेत का?
नाही सर, पण आन्सर काढलंय.
किती आलं रे?
1.28 FC आला, 1.28 किलोहर्ट.
हा. आणि हा सी किती घेतला?
0.01च घेतला.
हा. आर किती येतो मग? आलाय का विशाल परत? गेला फिरायला? विशाल विशाल कुठे? Okay. So with V out upon V in to be 0.01, F to be 120. Solving this, I get FC to be 11.999. 11.99 or 1.99. You are getting 1.28, no? Check the answer. I am getting 11.99. Check out the answer. Recheck it whether I am wrong or you are wrong. Can you see this answer? Is it visible? Is this visible?
Yes, sir.
So we check these calculations then. Am I correct or wrong somewhere?
नाही सर बरोबर आहे तुम्ही. आमचं चुकलं होतं थोडं एका जागेवर. So I'm getting R as 1.326 kilo ohms. And the nearest value is 1.33. Okay. The standard values you must remember actually. Table of standard values you must know. And now 30 kilohertz is the given frequency. Find out V out upon V in. With Fc known and F given to be 30 kilohertz. Fc is 11.999 kilohertz. F is given as 30 hertz, 30 kilohertz. Find out the value of V out upon V in. If a 30 kilohertz signal is given to the filter, a high pass filter, our high pass filter, what will be the gain or attenuation, whatever it is? Taken this down or calculating you? Are you calculating? Calculate V out upon V in using this formula with F is equal to 30 kilohertz and Fc is equal to 11.999 kilohertz. This is 30 kilohertz signal. What is the attenuation? You have to find out attenuation this V out upon V in. Okay, someone has typed the answer out something. काय झालं प्रियंका? 0.928. Let me check then. Yes, 0.928. Okay, so this is the answer then, 0.928 or 30 kilohertz, 92.8%. Yes. No, this is percentage term. 90, Devarshri, this is percentage, not hertz. It is V out upon V in. Okay, attenuation है. Attenuation 92.8%.
Yes, sir.
It doesn't have unit of frequency hertz, right? So let's move on then. Write down this for homework. No, this was okay. This is homework. Note it down. This is homework. Write it down. I'll check it in next lecture. Write down. A high pass filter is found to attenuate a 1 kilohertz signal by 20 dB. What is the critical frequency? FC. Right? So let's move on then. Let's start. Next type of filter, band pass filter. Okay, as the name suggests itself, it allows a certain band of frequency and blocks all other remaining frequencies. Band pass filter can be said to be a combination of both low pass and high pass filter. Okay, input signal low pass and high pass. So it will pass some low frequencies, this will pass some high frequencies, and the range of frequencies between high pass and low pass will give you the band of frequencies. Okay. Where are the applications? See, one of the applications in audio. Sometimes it is necessary to pass only certain range of frequencies. This frequency range does not start with 0 hertz or end at very high frequencies, but these frequencies are within certain range, either wide or narrow range. So these bands of frequency are commonly termed as bandwidth. Okay, so there is this one is and here are the characteristics of band pass filter. Then these are the ideal characteristics of low pass and high pass. Low pass and high pass. This is high pass. This is low pass, and when they are combined, it becomes a band pass. Okay, so this is F1 for high pass. This is F2 for low pass. Okay, this is F1 for high pass. This filter is stopping low frequencies, and this filter is stopping high frequencies, but their cutoff frequencies are different. If the cutoff frequencies are both are same, then up to this all frequencies will be uh, stopped, and after that all frequencies will be stopped. Okay, so we have a range of f2 minus f1 in which all the signals will be passed. Okay, this is low pass and this one is high pass. So this is stop band, this is stop band, and this is pass band. Okay, in practice such strict cutoff frequencies will not be possible. So this is high pass with this cutoff frequency, low pass with this cutoff frequency, and combined, then this will be FL and FH, right? Okay. So combination of low pass and high pass will have two cutoff frequencies, right? And characteristics will be something like this. Then 0.707 or minus 3 dB frequency, right? Minus 3 dB, and corresponding to that, this is high pass cutoff. FL is high pass cutoff. FH is low pass cutoff. Okay, so this is low pass. R here and C here is low pass. C here and R here is high pass. So they are connected in cascade, one after the other, right? So this forms a band pass filter. Okay. Lower cutoff frequency defines the frequency below which the ratio of V out to Vi is down by 3 dB. Higher cutoff frequency defines the frequency above which VO upon Vi is down by 3 dB. The frequency range between is called as band pass band rather. And once again, the cutoff frequencies, the similar one because one is low pass, one is high pass. Okay, so lower frequency FL is of high pass circuit. Please note, FL is of high pass circuit, whereas FH is of low pass circuit. Okay, so FL is given by 1 upon 2 pi RH and CH of high pass circuit, whereas upper cutoff frequency, higher cutoff frequency FH is given by, it is of low pass filter, this combination, and it is given by FH is equal to 1 upon 2 pi RLCL. Okay, this RL and this CL. So do not get confused. FL is of high pass and FH is of low pass. They are termed like that because this is higher frequency and this is lower frequency. That's why they are called as lower and higher cutoff frequencies. Otherwise, this corresponds to high pass filter and this corresponds to low pass section of the filter. Okay. Because the two filters, low pass filter is succeeded by high pass filter, they are connected in cascade, then the second stage may be loaded by the first stage. That is, low pass filter may be loading the high pass filter. To avoid this, we must have care must be taken, and for this, what we define is loading constant R. Okay, it is the ratio of high pass filter resistance to low pass filter resistance. So small r is defined as RH upon RL. RH is, where is RH? This is RH and this is RL. So RH upon RL gives the loading constant R, right? So this R must be sufficiently smaller, okay, as small as possible. What are the values then? We will see. To provide a good pass band, it is essential that the cutoff frequencies be as far apart as possible. Okay, band should be wide, and the resistance ratio R should be below 0.0. It should be less than 0.01. Okay, and as usual, we want V out upon V in, the gain or attenuation of the filter, total filter. It is given by FH into F. FH into F divided by root of F square minus FH FL whole square plus FL plus 1 by R, where R is RH upon RL, into FH square into F square. Okay, F is the given frequency, this and this, whereas FL is the cutoff frequency of high pass filter, FH is the cutoff frequency of low pass filter. Okay, so this is the formula for V out upon V in, gain or attenuation for a particular frequency F, right? So here is an example. So this is an example. Okay, today I will share this presentation PPT with you, and whatever is this problem or the band reject filter, you do it at home. I am putting it as homework then. Okay, time is over. I am winding up the lecture. So what I am doing is this PPT I will be sharing with you, right? And then rest of the part, design of this and design of band reject filter, I am putting it for you as a homework. Okay. So in next lecture we can start the operational amplifiers and active filters, right? So let me mark the attendance now. क्या हो गया, कौन निकल गया? विशाल आला का रे? विशाल,
हा सर बोला ना.
अरे कुठे गेला होता?
सर नेट गेलं होतं.
Okay, let me mark the attendance. Okay, attendance has been marked then. Okay, so rest part of this, the numerical problems of band pass filter and whole of the part of band reject filter, I'm sharing the PPT. Okay, do it at home then. In Thursday's lecture, we will start operational amplifiers and active filters. Okay, so I'm winding up now. Thank you very much, and always we will be solving at each step the problems. So notebook, pen, and calculator should be there. Okay, I ask you to solve any one sitting on the video. Please note. Okay, thank you then.